Hello, 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 and welcome back to this lecture series. I hope that you are doing well. My name is Professor Andrew Timming, and I am herein extending a very warm welcome to you, those of you who are tuning in to this lecture, which is the second in a series of lectures looking at the chi-square test, primarily at the chi-square test, which is a non-parametric statistical test that I've introduced in Chapter 7 of the textbook. So you already have some familiarity with the chi-square test because we introduced it in the first lecture of this lecture series. If you haven't listened to the first lecture, please pause now and go back and listen to that one first, because this one won't make a whole lot of sense unless you've had the necessary background from the previous lecture. And what we'll be doing in the context of this lecture is we will be calculating the results of a chi-square test. And we'll be doing that by hand, again, in a very step-by-step basis. Now, as I've said before, and I'll probably say again, with very large data sets, we wouldn't be expected to do any of the maths by hand. That's why we have statistical software to do the maths for us. But I think it's important for some of the simple bivariate tests that you have an understanding of the mathematics underlying the tests, so that when you run these tests on SPSS or whatever statistical software you're using, you'll understand what's going on. Okay, let's begin then. Okay, and here you can see the textbook that we are using in this lecture series. It's entitled Applied Statistics, Business and Management Research, a textbook that I wrote recently, and I very much hope you have enjoyed reading. If you haven't read Chapter 7 yet before listening to this lecture, I would urge you to press pause and read through the chapter, because the lecture will make a whole lot more sense if you've already read the chapter and have the necessary background. All right, let's dive right into an example of the chi-square test, shall we? So first things first, let's think about how we might want to frame a chi-square test. Now, you'll recall from the previous lecture that a chi-square test is a non-parametric test that essentially looks at whether two categorical variables are related to each other or whether they are independent from each other. Now, you can use nominal variables in a chi-square test. Both can be nominal. You can also use ordinal variables, as long as there are not too many categories. But I think for beginners, it probably makes sense to look at a simple 2x2 contingency table to think about how to calculate a chi-square test. So what you see in front of you is what we refer to as a cross tabulation or a contingency table. And this is just a purely hypothetical table. There's no actual data in here, but I present this to you just so you can get an understand of how we conceptualize the chi-square test and the calculation of the chi-square statistic. So you can see that in the rows we have our independent variable, and in this case there are two groups or categories in that variable. There's category A and there's category B. And similarly, you can see in the columns we have our dependent variable in this test. And again, this variable has two categories, category A and category B. Now, along the periphery, you can see the totals, the sums of the columns and the rows. So this is the outside of the box. What I want you to focus on at this point are the cells, the four key cells in the center of this table. These cells are labeled AA, AB, BA, and BB. And what these cells represent are the cases in your sample that fit at the intersection of the categories of your independent and dependent variables. Okay, so with this framework in mind, Let's now move on to look at an example with actual data involved. What you see in front of you is an example based on purely hypothetical data, right? These aren't real data points. I haven't actually gone out and administered a survey to psychology majors and engineering majors and asked them to rate their people skills. These are just figures that I've thrown together for illustrative purposes so that you can get an understanding of how we calculate and interpret a chi-square test. So you can see the research question at the top there. It's, are psychology majors better at dealing with people than engineering majors? And this research question should be familiar to you because we discussed it briefly at the end of the previous lecture. So let's take a look at what the data are telling us here. So we have our independent variable in the rows. That would be, what is your major? Are you a psychology major or are you an engineering major? And then we have our dependent variable in the columns. So that is, are you good at dealing with people or are you bad at dealing with people? And again, you can see in the 4 key cells the intersections of those categories. So we have 72 psychology majors who report being good at dealing with people. And we have 58 engineering majors that also report being good at dealing with people. And similarly, we have 63 psychology majors who report being bad at dealing with people. And we have 81 engineering majors that report being bad at dealing with people. And if you add up those 4 numbers, you get the overall total, which you can see in the bottom right-hand corner of this table. So we have a sample of 274 individuals. Now, I've taken the liberty of adding up the row and column totals. So if you take 72 plus 63, you get 135. If you take 58 plus 81, you get 139. And then vertically, if you take 72 plus 58, you get 130. And 63 plus 81, you get 144. So with this basic information, in other words, with the data in the 4 key cells as well as the marginals, we are able to calculate a chi-square statistic. So how do we do that? Right. So what we have in the previous table are the observed frequencies. So these are the frequencies of cases that we are able to observe in our sample. What we need in order to calculate a chi-square test are the expected frequencies, right? So to calculate the expected frequencies, what we need to do is we need to multiply the row total by the column total and then divide by the overall total, all right? And what we're doing in generating these expected frequencies is looking at what we might expect if there was absolutely no relationship between the 2 variables, right? So if they were completely independent of each other, these expected frequencies are what we might expect, all right? So I have taken the liberty of doing these calculations for you, although I would urge you to double check my math. Maybe I've made a mistake. You can see the expected frequencies here in parentheses in the table, right? So for the first expected frequency at the intersection of psychology major and good at dealing with people, I've taken 135, which is the row total, multiplied that by 130, which is the column total, and then divided by 274, that gives me 64.05. And similarly, if you go over 1, so we're looking at the intersection of psychology major and bad at dealing with people, I've taken 135 times 144, which is the column total, and then divided that by 274. That gives you 70.95. And then for engineering major good at dealing with people, I've taken 139 times 130 divided by 274. That gives you 65.95. And then for bad at dealing with people, I've taken 139 times 144 divided by 274. That gives you an expected frequency of 73.05. So with all the data that we have in this table in its current format, we're able to use the chi-square equation to calculate the chi-square statistic. Let's do it. All right, so the calculation of a chi-square statistic is actually quite simple if and only if you take it step by step. If you look at the equation itself, it might be a bit intimidating, but as is always the case in this course, we'll be taking it step by step so that you understand how to calculate it and you understand the easiest pathway for calculating a chi-square statistic. So take a look at the equation in the top left. Essentially what we're doing is we're summing together the observed frequencies minus the expected frequencies squared and then dividing that by the expected frequencies. So first thing we need to do is remind ourselves of what the observed frequencies, that's F sub O there. So we have our observed frequencies of 72, 58, 63, and 81. And you'll remember in the previous slide, I calculated our expected frequencies corresponding to those numbers as 64.05, 65.95, 70.95, and 73.05. So with that information, we simply plug in the values. So the next row down, I've plugged in the observed frequencies and the expected frequencies, squared them, and then divided them by the expected frequencies, and then simply added them up. So the next row down, this is the third row, I've simply taken the observed frequencies and subtracted the expected frequencies to give you the relevant numbers. And then in the next row down, so this would be the fourth row, I've squared those numbers for you. So we have our observed frequencies minus expected frequencies already squared. And then in the next row down, we simply carry out the calculations. So we take observed frequencies minus expected frequencies squared, and then we divide that by the expected frequencies, and then simply add up the four numbers corresponding to each of the four cells. So if I've done the math correctly, I get a chi-square of 3.69. All right, what does that mean, a chi-square statistic of 3.69? Let's take a look. Okay, so we've calculated a chi-square statistic of 3.69 or 3.7, depending on how you might want to look at that. And then the question is, what does that actually mean? So in and of itself, that statistic doesn't mean that much. It's similar to the T statistic that corresponds to the t-test that we've looked at and the F statistic that corresponds to the ANOVAs that we've already looked at. The statistic in and of itself doesn't tell us much. What we need is the p-value that accompanies it to tell us whether or not the result is statistically significant and therefore generalizable. Now, it's important to remember that a larger chi-square statistic generally corresponds to a lower p-value, which in turn generally corresponds to a greater likelihood of being able to generalize the results of our sample to our population. Now, in order to come up with the p-value, we need to look at the various parameters of the test. And fortunately, SPSS will do this for us, right? So the p-value in conjunction with the chi-square statistic will depend on the number of cases in the test and the degrees of freedom. Again, luckily, SPSS will do this work for us, so we don't have to do it ourselves. So I've taken the liberty of generating a p-value using this test, this particular test in SPSS, and I've calculated a p-value corresponding to a chi-square statistic of 3.69 of 0.054. Interesting, this p-value, isn't it? It's almost statistically significant. So remember, statistical significance is when p is less than 0.05. This is just ever so slightly greater than 0.05. And I've picked this example intentionally and deliberately because it teaches an important lesson, which is that we have to maintain hard and fast rules and sticking to the p-value cutoff. As much as we'd like to say it's almost significant here, we can't. The result that we're looking at now is that this result is not statistically significant. No matter how close it is to the cutoff of p is less than 0.05, it's still not statistically significant. So our conclusion in this particular test is that there is no relationship between these two variables. There's no relationship between your major, whether it's psychology and engineering, and whether or not you're a people person. Again, bear in mind that these are hypothetical data, not real data. So now that you've calculated a chi-square statistic by hand, the next thing you should do is experiment a little bit with chi-square on SPSS. And I've given you some key points here that you can rely on when you do your SPSS chi-square statistic tests. So the first thing you want to do, as similar with the previous test that we've looked at in this course, is look at your descriptive statistics and the frequencies of the independent and dependent variables. So before you actually do the test, get a sense of what the basic descriptive statistics tell you about these variables. Then to actually carry out the test, you simply go to Analyze, Descriptives, and Crosstabs. Crosstabs is short for cross tabulations. Might make sense to request charts so that you can help to essentially look at the data visually. That sometimes gives people a better understanding of what the data are telling you. And you might want to also request percentages in the tables, typically in the columns when your dependent variable is listed in the columns, because the percentages will make it easier to interpret the relationships between the two variables. In this case, in the exercise I've given, I didn't request percentages because the results were not statistically significant, but if they were significant, that would be the next thing I would do, is to request the column percentages to find out where exactly the differences lie. And lastly, you can also request effect sizes using Phi or Kramer's V. There is another non-parametric test that I'd like to introduce to you briefly. It's called the ManWhitney U Test. It is a non-parametric test similar to the chi-square test, but it's a bit of a hybrid. I guess that would be the best way to describe it. So the ManWhitney U test is quite similar to the independent samples t-test that we looked at previously. But you'll recall that the t-test is a parametric statistical test, meaning that it is predicated on the dependent variable being normally distributed, in other words, being bell-shaped, whereas the ManWhitney U test is a non-parametric test, right? But it acts a lot like the t-test. So it requires a two-category independent variable, just like the t-test, but instead of using scale variables, it uses ordinal dependent variables. So one of the advantages of the ManWhitney U test is that it's quite useful when your sample size is small, and it therefore, as a result of the small sample, your ordinal variable doesn't appear normally distributed. And the results of a ManWhitney U test are essentially a ManWhitney test statistic as well as a corresponding p-value, and that p-value would tell you whether or not you can generalize the results from your sample to your population. Okay, so let's briefly review what you learned in this chapter. In chapter 7, we looked at the concept of a non-parametric statistical test. We've looked at the example of a chi-square fitting that category, as well as the ManWhitney U test. And what makes a non-parametric statistical test non-parametric is that it is not predicated on a normally distributed curve. The chi-square test that we focused on primarily is really nicely suited to particular research questions that involve nominal and ordinal variables. It is not a suitable test if you have scale level variables in your data set. It works well with nominal and ordinal variables, but again, I would point out that the fewer the categories here, the better. So generally speaking, you don't want to have any more than, say, 4 categories per each variable, your independent and dependent variable. And the reason is that it becomes quite difficult to identify patterns when you have data with lots of categories. And then very briefly, we looked at the ManWhitney U test, which is similar to the independent sample t-test. It requires an independent variable that's nominal with only 2 categories. But in the case of this test, the dependent variable is ordinally measured. I'd like to ask you now just to take a few moments, press pause, and either individually or in groups, if that's feasible, have a look at these 6 discussion questions. They should help you further understand the material that I've presented so far in this lecture. And thank you very much. Thank you for paying attention. Thank you for bearing with me. And I look forward to seeing you soon. Bye-bye.